All right, so we're going to continue from the acid-base unit. And yesterday we talked about the pH of strong acid and strong base, which was fairly simple to calculate. It's just negative log of hydronium. So today we're going to talk about the pH of weak acid and weak base, which involves Ka and Kb. So this is a little bit more complicated because now there's an equilibrium. So just recall that the strength of an acid, it's only dependent on its ability to ionize in solution. It has nothing to do with its pH. If you have a strong acid and it's concentrated, you should have a low pH, very acidic. And a weak acid that is dilute will have a high pH. Okay. However, if you dilute a strong acid, you could get the pH to rise. And if you concentrate a weak acid, you can drop the pH. So a strong acid could have lower pH than a weak acid. It depends on its concentration. And it is the concentration of hydronium that results in the pH. So when you dissolve a strong acid in water, it is not in equilibrium. It is 100% ionization. All right, everything is reacted, and all of the acid HA will become A minus, and it will ionize 100% to produce the same amount of hydronium. So as a result, you can calculate hydronium concentration very easily from the balanced equation. It is exactly equal to the original concentration of the acid. So all you have to do is negative log, and you're done. If you have a weak acid, then you have a problem because it is not 100% ionization. Not all of the acid will react to produce hydronium. Only a small percentage will react. Well, so how much hydronium would you have? You have to calculate that using the Ka value. Okay, the Ka determines the extent of the ionization. So you have to perform a calculation with an equilibrium on the concentration of hydronium in order to calculate hydronium, and then negative log of hydronium will get you the pH. So you're going to need the Ka and the Ka expression. Okay, so let's actually look at an example on Ka calculations and how exactly does this work. So here goes. Calculate the hydronium ion concentration and the pH of 0.1 molar acetic acid. And Ka for acetic acid is 1.8 times 10 to the negative 5. All right, in order to solve for the pH of 0.1 molar acetic acid, you will have to write the equilibrium equation for dissolving acetic acid in water. What is acetic acid? It doesn't really tell you in the question. Acetic acid is quite a common acid. It is the same as ethanoic acid. SCH4U. Because it's a common acid, the question doesn't really give you the formula. If there is a weird acid out there that nobody knows the formula to, the formula will be provided. So you mix acetic acid and water. Acetic acid, being the acid, will donate a proton to the water, and it will become acetate, so CH3COO with a negative charge. And then water will become H3O plus, taking the proton. Then you will draw an ice table based on your equilibrium equation. And the initial concentration of the acid is 0.1 molar, so you have 0.1 molar for the initial and 0 for the products because you didn't react yet. The change will be X because you don't know how much reacted. That's what we're trying to figure out. So you minus X from the reactant and you plus X in the product, and the ratio is just 1, 1, 1, 1. So you don't need a coefficient. Equilibrium, you just add them up. Initial plus the change, so it's 0.1 minus X. For the products is X and X. All right, so this is exactly the same as the equilibrium calculations that we learned before. All right, so next step, you're going to need Ka. You need to solve for X, so you need Ka. So the Ka expression is product divided by reactants. Everybody should know how to do this at this point. All you have to do is sub in the values for Ka and then sub in X, and you calculate and solve for X. you could use the quadratic formula for this, but that is very tedious. Instead, we will assume that x is a tiny number, so subtracting x won't matter. You can pretty much always assume for acid-base calculations, because acid and base, if they're weak, they're all going to have very small Ka and Kb values, which would make this work. If you divide the initial concentration by a really small Ka, in this case is 1.8 times 10 to the negative 5. If you divide by 10 to the negative 5, what you're going to get? 10,000. So that's a huge number, way greater than 100. So this justifies our assumption. So you can simplify the denominator from 0.1 minus x to just 0.1, because subtracting the small number makes no difference. It is time to rearrange and solve for x. If you just rearrange this, x is approximately equal to square root of the Ka, which is 1.8 times 10 to the negative 5, times the initial concentration, 0.1. All right. A calculator will get you 1.342 times 10 to the negative 3 moles per liter. So that's x. The question asks for two things. One, it asks for the hydronium concentration. So there we go, you have to solve. Hydronium concentration is equal to x. You round to the correct sig figs because that is one of the answers we're looking for. So it's 1.3 times 10 to the negative 3. The question also asks for the pH. So you have hydronium. Use the formula for the pH, which is negative log of hydronium. And you have to use the unrounded number because we're not done with the calculation. So negative log of 1.342 times 10 to the negative 3. You put this in your calculator, you should get 2.89. All right, so that's it. The concentration of hydronium is 1.3 times 10 to the negative 3, and the pH of acetic acid is 2.89. Does that make sense logically? Acetic acid, being an acid, has a low pH. That makes perfect sense. All right, if you get like a huge number, if you get like 7, acetic acid can't have a pH of 7, that's neutral. Or if you have 9, then you know you got it wrong. If you have a small number, then yeah, you're probably right. Does that make sense for everybody? It's the exact same calculation for equilibrium, except we apply it to an acid. We solve for H3O+, and then take the negative log of that to get the pH. All right, so I'm going to have you work on example 2, which is basically the same thing as example 1. Different equation, different Ka, calculate the hydronium concentration and pH of 0.25 molar solution of barbituric acid. I'll give you around 5 minutes for this, and I'll take this up in 5. All right, so I'm going to take this up. Barbituric acid, that thing, and organic acid used to manufacture hypnotic drugs and some plastics is a weak acid with a Ka of 9.8 times 10 to the negative 5. An industrial process requires 0.25 molar solution of barbituric acid. So calculate the hydronium concentration as well as the pH of the solution. All right, so step 1, you have to write the equilibrium equation. To write the equilibrium equation, you simply add it to water, and the product will be just moving one hydrogen from your acid to the water to make H3O. 9 times out of 10, your acid would start with hydrogen. Okay. You would have many hydrogens, but one of them will be special. You put it in the front just to show you that this hydrogen can be removed. So you get rid of the first one, you stick it on water to make it H3O, and there you have it. Those are your products. Okay. If you remove a hydrogen from something, because it's a proton, it's positive, you now have a negative charge. So once you have the balanced equation, you draw an ice table from the balanced equation. You fill that in. Initial concentration is 0.25, 0 for the products since you didn't make the products yet. The change is X. Okay, you don't know what that X is. So, equilibrium would be just the sum of the initial and the change. Okay, so far so good. All right, so the Ka expression is here. You would plug in all your numbers. You know what the K is. You sub the X's in. Oh, whoops, I screwed up the PowerPoint there. So assume that X is so small that if you subtract X, it doesn't make a difference. If you assume that, well, you have to justify. So to justify, you take your initial concentration, you divide by the Ka. If you divide by like 10 to the negative 5, you're going to get a huge number. So obviously, it's going to be bigger than 100. So we justify our assumption, and you can have a simplified version where the denominator is just 0.25. Get rid of the X. Now it becomes very simple. X is equal to the square root of 9.8 times 10 to the negative 5 times 0.25. Right? And before I go on, I just want to show you a shortcut. You can skip all this. I don't recommend you do, but let's say you're very lazy, right? You're running out of time, and I just want to get to the answer quick. Well, here's a rule of thumb. The concentration of H3O in an acid, in a weak acid, is equal to the square root of coca. What is Co? Well, C, that is not an O, that is actually a 0. That means initial concentration, so C initial, multiplied by the Ka. So let's call it coca. Hydronium is the square root of coca. That is with the assumption that X is so tiny, it doesn't matter. And so you can skip the ice table, skip whatever, just go directly to here. You know the initial concentration, the question should tell you. You know the Ka, the question should tell you. If the question doesn't, look on the table. Just square root, multiply those numbers, boom. But on the test, I don't recommend you do this. I mean, you're probably going to get the right answer, but if it's a paper test, then you should show all your work. This is like multiple choice question. You're too lazy. Here's a rule of thumb. So X is approximately equal to 4.950 times 10 to the negative 3. All right. And the hydronium concentration, you just round to 2 sig figs. Okay, that's probably a rounding error right there. That should be 5.0. I don't know what I was thinking. I should probably fix that. Are you good? That is hydronium ion concentration. To calculate pH, pH is negative log hydronium. You sub in the unrounded version of this. So it's negative log 4.950 times 10 to the negative 3, and calculator pH is 2.31. 2 sig figs for the pH. Okay, 2 decimals because the concentration has 2 sig figs. Does that make sense? pH is 2. All right, you have an acid. Of course, the pH is going to be low. So yes, your answer does make sense. All right, we good? I got 2 more examples, example 3 and example 4. I'll give you some time to work on those as well. And once you finish both, I will take them up. Okay, start when you get to base. I will explain how to do base. I'll give you some more time, around 5 to 10 minutes, to work on the next 2 examples. All right, so here's example 3 and example 4. So in example 3, you measure the pH of 0.100 molar hypochlorous acid and find it to be 4.23. What is the Ka of hypochlorous acid? So you're asked to find the Ka. So you have to do the opposite of what you've been doing, but you still need the equilibrium equation. Okay, in order to find the Ka, you need to use the ratios of the products and the reactants. So you need to calculate what the product concentrations are and the reactant concentration. So you write the equation, hypochlorous acid plus water, well, that's hypochlorite. You lose a hydrogen to water to become hydronium. So determine the concentration of H3O at equilibrium. If you remember math class from advanced functions, When you want to isolate for H3O, it is equal to 10 to the power of negative pH. And the pH is 4.23, so the answer should be 5.888 times 10 to the power of negative 5. That is the concentration of H3O. Knowing this, you can fill out a nice table. The initial is 0.1, given to you in the question, 0 for the products. Change is X, and equilibrium, you just add them up. But we know what X is. Okay, we know that X is equal to hydronium, which is equal to OCl minus, and we calculated that to be 5.888 times 10 to the negative 5. So you can then use X to calculate the initial the concentration at equilibrium of the acid, so which is 0.1 minus 5.888 times 10 to the negative 5. All right. And of course, you can write the Ka expression. You can plug all of this information in to solve for the Ka. So that is 5.888 times 10 to the negative 5 squared divided by 0.1 minus 5.888 times 10 to the negative 5. Notice that I didn't round excessively. I used additional digits for more accuracy. You put this in your calculator all in one step. Ka should be found to be 3.5 times 10 to the negative 8. All right, does that make sense, everybody? Is that all you got? Is that what you got for everyone? All right, so example 4. Example 4, you have basically the same type of question. Calculate the Ka of the 0.050 molar solution of nicotinic acid, which is that, with a pH of 3.08. And nicotinic acid is one of the B vitamins, a dietary requirement. Okay, that sentence is very useless. So to do this one, you would write the equilibrium equation. Whatever this nicotinic acid, you start with H, so you're going to lose that H to water. Determine hydronium at equilibrium. Well, it's the same thing as before. 10 to the negative pH, and it's 10 to the negative 3.08, so you have 8.318 times 10 to the negative 4. So that is the concentration of hydronium. You got that from the pH. Same idea, fill out the ice table. Initial is 0.050. You have no products in the beginning. Change is X, we don't know that. And at equilibrium, you add up the first two rows. We do know what X is. X is hydronium, which we calculated to be 8.318 times 10 to the negative 4, which is equal to the conjugate base. Okay, and you can use X to calculate the concentration of the acid at equilibrium to subtract from 0.05. And you can sub all of this into the Ka expression. Notice that this is the exact same format. Nothing changed except the numbers. So X squared, that would be 8.318 times 10 to the negative 4 squared divided by 0.05 minus 8.318 times 10 to the negative 4. You have a calculator, put everything in the calculator at once. You get the Ka. 1.4 times 10 to the negative 5. So notice that there's 2 sig figs because the initial concentration has 2 sig figs. All right, so therefore the Ka of nicotinic acid is this. Does that make sense for acid calculations? All right, good. So if you've been paying attention in equilibrium, this should be fairly simple. It is the same thing with a tiny twist. If you struggled with equilibrium, you might find this difficult, so you have to work a little bit harder to catch up. Base is basically the same thing as acid in terms of strategy. A weak base is an equilibrium. Okay, you need to calculate the concentration of OH, which you don't know. It's not equal to the base because there's a Kb. It's not 100% protonated. So the Kb will tell you how much of the base will become of the OH. You need to calculate Kb and then write the Kb expression and use that to solve for the OH. Once you solve for the OH, you can solve for the pH. using negative log. Okay, two differences though. You might not know what the Kb is. If the question doesn't give you the Ka, have to do. And then negative log of OH is not pH, this is POH, so you have to subtract it from 14. So it's the same thing, except we have two extra steps, but otherwise, same equilibrium, same calculation. So let's look at example 5. Calculate the pH of 0.100 molar aqueous solution of hydrazine, I believe is rocket fuel, which is a weak base. The Kb for hydrazine is 1.7 times 10 to the negative 6. All right, so for this, you have to write the equilibrium equation and then set up ice table. I'll show you how to do this one, and then I'll have you guys work on the last example. To write the equilibrium equation for a base, you have N2H4 plus water. A base will accept a proton. It will take a hydrogen from the water and stick it onto itself. You have N2H5. Now you have a plus charge because you got an extra proton. Water becomes OH minus. That's the indicator of a base. Okay, you see the OH minus in the product. Okay, this is a base. Set up the ice table. If you have your balanced equation, you can just set up the ice table right the first row as initial, 0.1 mole per liter and 0,0. X, we don't know. Equilibrium is just the sum of the first two rows, so it's 0.1 minus X with X and X as the product. So once you have the ice table, you have the Kb, you can solve for X. You write the Kb expression, products over reactants, and you simply substitute everything in. The Kb, substitute 1.7 times 10 to the negative 6, and then all the X's on the right side. We are, of course, going to assume that X is tiny, so this is insignificant. We justify it by dividing the concentration of the base in the beginning with the Kb. And if the Kb is 10 to the negative 6, you're going to get a huge number. So, of course, it's bigger than 100. So we justify our assumption. We can simplify the denominator by dropping the X. Right? And you isolate X now, square root of the Kb times initial concentration of the base. You put this in the calculator, you get 4.123 times 10 to the negative 4 moles per liter. That's X. What is X? X is OH. Okay, you can check with your ice table. It tells you clearly what is X. OH, that's exactly what you need. So OH is 4.123 times 10 to the negative 4. We need to calculate pH from an OH. So first you have to calculate POH because hydroxide can only get you POH. And then you will subtract that from 14 to get the pH. Okay, and the negative will cancel. You have 14 plus log of the hydroxide. And your calculator should give you 10.62. Two sig figs for this. The decimals are the significant figures, only 2 decimals, because in your concentration you have 2 sig figs. Does this answer make sense? Hydrazine is a base, and as a base it has a high pH, 10. Yeah, that makes sense. So this is probably correct. Notice that this is exactly the same as an acid, except that last little step. All right, so last example, example 6. Work on this on your own, and I'll take this up later. So you have highly concentrated ammonia solutions used by industries are sometimes called liquor ammonia. Okay, useless sentence. Calculate the pH of 15 molar solution of ammonia. All right, so good luck with that. I'll come back in 5. All right, so last example. You're trying to find the pH of 15 molar solution of ammonia. 15 molar is really, really high. Okay, that is an extremely high concentration of ammonia, and this should be pretty deadly. So first you write the equation for the reaction. That would simply be ammonia plus water. You get ammonium and OH. Ammonia will gain a hydrogen from water to have NH4 plus ammonium. And then you make OH, which is what a base should do. Then you set up the ice table. The first row, ammonia, you have 15 molar, 0 for the products. Okay, X is your change, you don't know what that is. And your equilibrium is 15 minus X, and then the products are X and X. So here's the KB expression. Products of a reactant, this is all good, except you don't know what the KB is. You need to solve for the KB. Kw is a constant. You always know what that is. Ka of the conjugate acid, NH4, can be found on the table. Okay, and it has to be the Ka of the conjugate acid. These must be conjugate acid-base pairs. Don't look at any other number. It has to be NH4 Ka. That happens to be 5.6 times 10 to the negative 10. You divide these two. The Kb of NH3 is 1.786 times 10 to the negative 5. So you have to calculate Kb and make sure you have extra digits for rounding purposes, so you have more accuracy. Finally, you can solve for X. You have the Kb and you have the Keq expression. You plug everything in. You assume that X is a tiny, tiny number. 15 minus this number is insignificant. Okay, because 15 divided by 10 to the negative 5, yeah, that's a small number. Also, that's a large number, greater than 100. So you justify your assumption. You simplify the denominator to just 15. You isolate and solve for X. It's the square root of Kb times the initial concentration. You can basically skip directly to this step if you're lazy. And X is 1.637 times 10 to the negative 2. You have to understand what X is. What did you just solve? Okay, check with the ice table. You just solved for the hydroxide concentration. OH concentration is 1.6 times 10 to the negative 2. You can then calculate the pH. OH is negative log of OH, so pH is 14 minus the POH. The double negatives cancel. You have 14 plus log of hydroxide, and you get 12.21. Okay, 2 sig figs, 2 decimals. Does that make sense? The solution of ammonia has a pH of 12.21, which is pretty high. Ammonia is a weak base. Normally, a normal household concentration and pH, you should get around like 9 to 10. 12 is significantly higher because the concentration is higher. So that's it. That's all we learned. How to calculate pH of weak acid and weak base. We need an equilibrium ice table. We need the Ka and the Kb values, and then take negative log of hydronium or hydroxide to find the pH or POH. This is a fundamental skill. The next 3 lessons will all require you to know how to calculate the pH of a weak acid or weak base. You need to know how to do this in your sleep. All right, any questions? All right, cool. I'm going to end this one.